Hello students, welcome to lesson 16 of module 4. Module 4 is on pavement design. So this lesson is about designing concrete pavements as per PCA and AASHTO design procedures. In the previous lesson, that is lesson 4.15, we discussed about designing concrete pavements as per Indian Road Congress guidelines, that is IRC 58 2002 version. We will see the similarities and differences between these two procedures that I am going to discuss in this lesson and the Indian Road Congress design procedure also. So the specific objectives of this lesson would be, after completing this lesson, the student is expected to understand the basis for the PCA and AASHTO methods for design of concrete pavements. PCA is the Portland Cement Association, and AASHTO, as we learnt in the earlier lessons, is the American Association of State Highway and Transport Officials. So we will understand, rather the student would be in a position to understand the basis for the PCA and the AASHTO methods for design of concrete pavements. They would be familiar with the concepts adopted by these two different agencies for design of concrete pavements. The students would be able to select appropriate traffic and material inputs for design as per these two different procedures, and they would also be in a position to carry out designs of concrete pavements as per PCA and AASHTO criteria. So the two design methods that we are discussing today in this lesson are those adopted by Portland Cement Association PCA method and the American Association of State Highway and Transport Officials AASHTO. We will first start with Portland Cement Association method, PCA method. The first set of guidelines as per PCA were published in 1984. The performance criteria and design criteria and the design methodology that was published in 1984 was based mainly on the performance data collected at the AASHTO road test. In fact, as I indicated, AASHTO road test had various types of pavements, flexible pavements, different types of concrete pavements. So the performance of different types of concrete pavements were observed during the AASHTO road test. That data and those pavements were analyzed, which subsequently led to different types of performance criteria for different types of pavements. So we have already seen AASHTO guidelines for design of flexible pavements. We will also discuss about AASHTO guidelines for design of concrete pavements in this lesson, but the same data formed the basis for most of the other design procedures such as Portland Cement Association also. The main failures considered in the PCA design procedure are fatigue cracking of concrete and erosion of foundation. So these are the two main failures. If you recollect, in the previous lesson on design of concrete pavements as for IRC procedure, there also we made a mention of erosion failure, but IRC does not make any specific design provisions for carrying out erosion analysis, but one provision that was made to handle erosion in IRC concrete pavement design was provision of concrete, rather paved shoulders of 1.5 meter width, but there is no specific analysis included in the IRC procedure for erosion analysis. So PCA considers two types of failures, fatigue cracking and erosion of foundations. Fatigue failure is the one in which the pavements fail by fatigue of concrete. Erosion failure is the one in which the pavements fail by pumping. We discussed about pumping in the previous lesson. Erosion of foundation leading to formation of gaps below the slab and joint faulting, joint being at different levels. For fatigue analysis, the critical stress, because if the load is placed in different regions of the slab, the tensile stresses that will be developed will be different. So, the critical condition of load position has to be selected. The critical stress condition is considered to be 8 stresses midway between the transverse joints. If you consider these two transverse joints, and if this is the longitudinal edge, which is the free edge, and next to this we have a shoulder. So, we are concerned about the edges that are developed along this edge. When the wheel load is placed close to the edge, with the tire impedance being tangential to the longitudinal edge, and it is away from these two transverse joints. So, that is what we mean by midway. So, this is the position of the load that we are concerned about. Edge stresses midway between the transverse joints in the edge region away from the joints. There are two cases that we consider, with and without concrete shoulders. This is what PCA considers. There are two cases. There will be concrete shoulders tied to the main slab or without tied concrete shoulders. Cumulative fatigue damage concept is used in PCA. Stresses due to warping and curling are not considered for fatigue analysis. These stresses are not added to the wheel load stress while carrying out fatigue damage analysis, because both of them happening throughout the year, throughout the life period, both the combination being additive is not possible. Sometimes it is additive, sometimes it is subtractive. So, the warping and curling stresses are not considered and they are not added to the wheel load stresses for carrying out fatigue analysis. The combined stresses due to warping, which occurs because of variation in moisture within the slab, and curling, which occurs because of the variation in temperature within the slab, are usually subtractive from load stresses most of the time. The fatigue damage is computed using this expression, where dr is the damage caused to the slab, cumulative damage, given as sum of n I divided by capital N I, where I varies from 1 to m. In this we have m is the number of load groups. Suppose if you have the axle load data and then you have grouped the axle load data into m groups, group 1 being say 0 to 4 tons, group 2 could be 4 to 8 tons, whichever way you classify it, you have 8 groups of load groups. Then Ni is the predicted number of repetitions for ith load group. What is the number of load repetitions of the ith group, say 0 to 4 tons, expected to be applied on the pavement during its service life period? This has to be available to us from traffic projections. So, small Ni is the number of load repetitions of group I. Capital Ni is the allowable number of repetitions for ith load group. That means, if you apply only the ith load group loads, say 0 to 4 ton loads only, how many repetitions of this load group the slab can handle before it fails? That is capital Ni. So, once you get this ratio for different load groups, you can sum up all those relative damages, and accumulated damage ratio should be smaller than 100% for the slab to be safe. This is the fatigue relationship considered for concrete. These relationships explain in terms of the stress ratio how many repetitions the slab can handle or the concrete material can handle before it fails in fatigue damage. As we have seen in the case of IRC guidelines, in fact these are similar guidelines, for different stress ratio conditions, different relationships are given correlating the number of repetitions concrete can handle for a given stress ratio before it fails in fatigue damage. As you can see in this slide, for different stress ratio values given by sigma by SC, where sigma is the stress, tensile stress in concrete because of the load under consideration, where SC is the tensile strength of concrete. We have represented this as stress ratio SR. So, if the stress ratio is greater than or equal to 0.55, the number of repetitions to fatigue failure NF is given as a function of stress ratio sigma by SC by this equation. For stress ratio range of 0.45 to 0.55, number of repetitions to failure of this load group are again given as a function of stress ratio. For n less than 0.45, it is assumed that the concrete is capable of handling infinite number of repetitions. For carrying out fatigue analysis, that means for calculating the wheel load stresses, the wheels placed close to the edge produce maximum stresses. Even if the loads are slightly placed away from the edge, the reduction in stress is significant. So, it is important to understand what percentage of wheel loads are going to be placed close to the pavement edge. All those loads that are placed even slightly away from the pavement edge, it is seen that the reduction in stress is significant and it is not going to be significantly contributing towards fatigue damage. So, we are concerned about those wheel loads which are placed very close to the pavement edge. Portland Cement Association PCA analysis indicates that considering only 6% of traffic, of the total traffic traveling in one direction, and assuming that all these trucks have their outer wheels placed in the edge region, produces the same cumulative fatigue damage produced by all the trucks positioned at different locations from the edge. For example, what we are trying to indicate is, if this is the pavement, so we can have, for example, at a given point of time, if this is how the vehicles are placed, if we put these wheels in exactly the same position, if this is a realistic practical positioning of vehicles, so the depending on the traffic intensity, depending on the facility that is available, all the wheels are not going to travel along the same path, they are not going to follow any particular path, they are going to be distributed across the carriageway width. One vehicle may travel along this path, another vehicle will travel along this path, another may take a slightly different path. So, the wheel load positions are going to be distributed across this width. So, if you put these wheel loads exactly in the same position and calculate stresses in the edge region, on the other hand, if you put only 6% of all these vehicular traffic, put them exactly in the edge region position as shown here, in both cases the edge stresses that are going to be computed will almost be similar. So, that is what PCA has worked out. So, to repeat this again, PCA analysis indicates that considering only 6% of traffic and assuming that all these trucks have their outer wheels placed in the edge region produces the same cumulative fatigue damage produced by all the trucks positioned at different locations from the edge. So, what is being implicated here is, what is being emphasized here is that we need to consider only a certain portion of all the truck traffic and then assume that these vehicles are being traveling, they are traveling with their outer wheels placed tangential to the outer edge, then analyze the slab only for those wheels. If the total traffic is considered, for example, if you are trying to consider the total traffic, assume all the 100% repetitions you are considering, then it can still be done, but the edge stress computed will have to be reduced by a factor of 0.894. That will be corresponding to the actual total cumulative damage that you can obtain. coming to erosion analysis, that is considered in PCA analysis, pavement problems such as pumping, faulting and erosion of foundation etc. are more due to the deflection than due to stresses in the slab. Deflection is the consideration that we have to be concerned about. If there are more deflections, there is going to be more amount of pumping, more amount of erosion and more faulting problems also are going to be likely to be there if the slabs deflect more. Most critical location for deflection obviously is a corner because of its discontinuity in two directions. That is when the load is placed in the corner region. Erosion is influenced by the type of joint. Obviously, if there is load transfer across the joint, the deflection is going to be lesser, erosion is going to be lesser. So, we have to consider what is the type of joint that is there, what is the type of load transfer mechanism, whether it is through granular interlocking or if there is a provision of dowel bars placed across the joints. So, we have to take all these things into account before computing what is the deflection and accordingly what is going to be the erosion damage caused to the foundation. So, for carrying out erosion analysis, the critical loading position as we just discussed will be the corner location. So, the load has to be placed in the corner region. This is one free edge, there is shoulder on this side, there is another free edge, this may not be exactly free, but there is another slab that is on the other side, there is a joint here. So, this is where some amount of discontinuity is there in both the directions. So, we have to place these wheel loads as close to the corner as possible. So, that is when we are going to be having maximum deflection in the corner region, that is the critical condition. Again, we will have to assess what percentage of total traffic will have their wheel loads positions in the corner region, whether it is 100% or part of that. This is the erosion criteria that PCA adopts to estimate how many repetitions the pavement can sustain before unacceptable levels of erosion takes place, before the slab or the foundation fails because of erosion failure. This is given as log n equal to 14.524 minus 6.77 into C1P minus 9 to the power 0.103. In this case, C1 is an adjustment factor to account for different types of subbases that are used. C1 will be 1 for untreated granular subbase and C1 will be 0.9 for stabilized subbase. The other parameter that we used here, P, is the rate of work computed as 268.7 into P square by H into K to the power of 0.73. This is a function of the pressure on the foundation under the slab corner. This is the pressure under foundation under the slab corner. H is the thickness of the slab and K is the modulus of subgrade reaction. So, the rate of work is a function of all the pavement parameters, thickness of slab and modulus of subgrade reaction and the deflection of the slab at the corner, which can be used to obtain the pressure as P equal to K W, where W is the deflection in the corner region because of load applied in the corner. K is the modulus of subgrade reaction because of the assumption that we made about the spring foundation. The reactive pressure is proportional to the deflection. Proportionality constant, as we know, is the modulus of subgrade reaction. So, if you can calculate the deflection in the corner region due to a load that is placed in the corner, then using this expression we can find out P, slab thickness has to be known, and K also is an input parameter. We can calculate the rate of work. So, substituting this in the above equation, we can find out how many repetitions of a given load the slab can sustain before it fails because of erosion failure. The percentage erosion damage caused, again, because here also we are going to have different magnitudes of loads and different magnitudes of loads would produce different amount of deflection. So, the erosion damage caused by different axial load groups will be different. So, we have to sum up all the damage caused because of all the groups of axial loads. So, this is how we do the summation. So, the total erosion damage is again a summation of a multiplication factor C2 small ni divided by capital Ni. C2 takes values of 0.06 or 0.94 depending upon what type of a shoulder is provided, whether it is without concrete shoulder or with a concrete shoulder which is tied to the main slab. Accordingly, C2 will take values of either 0.06 or 0.94. The percentage erosion should be less than 100%. Again, small ni as discussed in the previous slide or as discussed in the case of fatigue damage analysis is the number of repetitions of group I, and capital Ni is the number of repetitions the slab can sustain as per the criteria given in the previous slide for a given load, because we can calculate the corresponding deflection for that load, and for that deflection for a given pavement system how many repetitions it can sustain can be obtained from the erosion criterion given in the previous slide. So, the total percentage erosion should be less than 100%. The design inputs that are to be obtained for carrying out design as per PCA analysis are about the concrete. We need to have the flexural strength of concrete represented in terms of modulus of rupture expressed as MR. We have to have information regarding the subgrade strength in terms of the modulus of subgrade reaction. We also have to have information in terms of the loading, magnitudes of axial loads, and also the frequency of axles of commercial vehicles. We are interested in only commercial vehicles. Normally, design period is considered to be 20 years. The flexural strength of concrete influences the fatigue behavior of concrete. Modulus of rupture determined at 28 days under third point loading. How this has to be obtained is also specified. Beam specimens have to be prepared, third point loading has to be conducted, and the modulus of rupture obtained from the test at 28-day period has to be used for design. Subgrade strength has to be obtained by conducting a plate load test. This is what is recommended by Indian Roads Congress also. The load per unit loaded area per unit deflection is the modulus of subgrade reaction. This we already know. PCA also suggests that K value can be estimated from California bearing ratio value of the subgrade or its R value. It also recommends that normal summer or fall K values should be used. Seasonal variation of K is not normally considered. These are the typical subgrade modulus of subgrade reaction values for different types of subgrade soils. For example, for plastic clay, one can expect a K value expressed in terms of pounds for cubic inch in the range of 50 to 100, whereas for gravels it can be more than 300. For cement or asphalt treated bases it can be more than 400. Sands and clays gravels 200 to 300, silt and silty clays 100 to 200. This is just an approximate idea of what could be the modulus value of K, modulus of subgrade reaction value of different types of soils. We may provide subbase to avoid mud pumping. Subbase can be untreated granular base or cement treated, especially for heavy duty highways, high volume roads. So, normally we provide granular subbase untreated either with cement or asphalt or bitumen. So, that is what is known as granular subbase, or we can also have cement treated base. If you recollect, IRC 58 recommends use of dryline concrete as subbase, especially IRC 58 is meant for high volume roads like national highways and other heavy traffic roads. So, dryline concrete is what is recommended there. So, PCA also recommends that you can either use a untreated granular subbase or cement treated bases. Where subbase is used, obviously the K value will have to be increased suitably. this is how we can increase the modulus of subgrade reaction of a given subgrade if a subbase is used, subbase of different thicknesses. This table here gives us guidelines about how to obtain the corresponding increased effective combined modulus of subgrade reaction for the two layers, subgrade and the granular subbase. This is for untreated subbase. If you provide a 6-inch untreated subbase over a subgrade having 100 PCA modulus of subgrade reaction, the combined effective modulus of subgrade reaction can be taken to be 140 PCI, pounds per cubic inch. Similarly, if we place a 12-inch subbase, granular subbase over a subgrade having a K value of 300 PCI, the effective K value can be taken as 430. Similarly, if cement treated subbase is used on subgrade, this is how to select the combined effective subgrade modulus of reaction. So, for different thicknesses, for different subgrade K values, the effective K values are given here. Other design parameters relating to traffic are, we have to select a design period or the traffic analysis period. This has to be selected on the basis of economic analysis of payment costs and services. Other traffic parameters are selecting number of heavy axle loads expected during the pavement life. These are to be derived from commercial traffic as percentage of average daily traffic, average daily traffic, average daily truck traffic in both directions, and also we have to have information regarding axle load spectrum. The traffic projections are to be made in the following manner. Design ADT will be a projection factor multiplied by the present average daily traffic. Projection factors normally range from 1.2 to 1.8 for annual growth rates of 2 to 6%. PCA also recommends usage of load safety factors, LSF, as we have done in the case of IRC 58 also. For different types of facilities, different load safety factors are given. As you can see here, for high traffic volume roads, load safety factor of 1.2. For moderate volumes of truck traffic, load safety factor of 1.1. For roads, residential streets, other streets where small volumes of truck traffic is there, load safety factor of 1 can be used. These are similar to the values that were adopted in the case of IRC 58. The other inputs that are required for design are, what is the type of joints that is provided, what is the type of shoulder that is there, concrete shoulder, unpaved, tight concrete shoulder. So, different PCA gives design provisions for different types of shoulders. Concrete flexural strength at 28 day has to be obtained, and the K value of subgrade or the combined modulus of subgrade reaction of subgrade and any granular treated or untreated base has to be available. We have to select a load safety factor depending on the type of facility. We have to have information on the axle load distribution. We also have to have projection about the expected number of repetitions of different axle load groups during the design period. The design method follows the following steps. For analysis, both for fatigue analysis and erosion analysis, separate tables are available, separate charts are available. Although if the program is available, one can do the analysis independently, but for somebody who is doing the analysis on the basis of tables and charts, a series of charts and tables are available in the PCA guidelines to easily work out what is the fatigue damage and also what is the erosion damage. Separate tables are used to evaluate fatigue and erosion damage. Equivalent stress tables are available, which give us for a given thickness of slab, say 4 to 14 inches thick, and for a given K value of foundation, either only the subgrade or the combined effective K value of subgrade and the base. We can find two values in the table. For example, for 4 inches and for a K value of 50, 825 and 679 are the values that are available, whereas 829 is the equivalent stress for single axle and 679 is an equivalent stress parameter for a tandem axle. So, the number on the left, that is 825 in this case, is for single axle. The number on the right, that is 679 in this case, is for a tandem axle. This table is for a case where no concrete shoulder is used, but a similar table is available for pavement with concrete shoulder. These stress analysis tables are, rather they were developed using a finite element program JSLAB for the following data. Modulus value of concrete was considered to be 4 into 10 to the power of 6 psi. Poisson ratio is taken as 0.15. Dole bars were considered. The dole bar dia was taken as 0.5 inches. The dole spacing was 12 inches. Modulus of dole support was taken as 2 into 10 to the power of 6 PCA. Spring constants were used to model the aggregate interlocking, and similarly spring constants were also used to model the joint between the shoulder and the main slab through this tight concrete shoulder. So, these are the spring constants that are used, 5000 psi and 25,000 psi. The equivalent stresses shown in the tables are edge stresses multiplied by 0.894. This is to account for the portion of loads placed close to the edge. So, it is assumed that we are going to be considering, rather we are considering only those loads which are going to be placed close to the edge. So, to account for that, the stresses are already multiplied by a factor of 0.894. Edge region is considered to be critical, and the stresses that are computed are for edge region. The single axle considered is 18 kip, tandem axle considered is 36 kip in this analysis. These stresses are corresponding to 18 kip single axle and 36 kip tandem axle. The fatigue analysis proceeds like this. We assume a trial thickness and determine equivalent stress for single axle, that is 18 kip axle, and tandem axle, that is 36 kip axle. We determine these from the tables for a given slab thickness, for a given K value, and for either single axle or tandem axle, as we have seen in the previous slide, we have equivalent stress values available for both single and tandem axle. So, we can select those values from those tables. Next, we compute stress ratio factor as the ratio for equivalent stress to the design MR. For the given concrete grade that we selected, we know the modulus of rupture value, that is the flexural strength of concrete. Once we know that, we have already selected the equivalent stress value from the table. So, equivalent stress divided by modulus of rupture gives us the stress ratio. Obviously, we will have one stress ratio value for single axle because we have a different equivalent stress value selected from the table for a single axle. Similarly, we will have another value of stress ratio for tandem axle because there is another equivalent stress value that is obtained from the table. For modulus of rupture value, we use 28 day strength. We estimate allowable repetitions NF from the following chart, which will be shown in the next slide. For allowable repetitions falling outside the range of the chart, it is assumed that the allowable repetitions are considered to be infinite. This is the chart that we are going to use to find out for a given axle load, whether single or tandem, how many repetitions the slab can sustain. So, once we select a single axle, say 20 kip, and then we have already worked out what is the stress ratio factor for single axle for the given pavement system, connect these 2 points, extend it to meet this line, and this is the value which gives us the allowable repetitions if this is the load that is going to be applied repeatedly. Similarly, for other single axles, we can find out what is the number of repetitions the pavement can sustain. So, the same thing can be done for tandem axle also. So, for both single axle and tandem axle, if you know the axle load groups, their magnitudes, we can find out the corresponding allowable number of repetitions using this chart. Similar analysis can be done for erosion also. We have tables available in PCA design procedure for finding out erosion factors. Again, these are function of slab thickness and the K value of the foundation. So, here also we have erosion factors, different erosion factors for single axle and then tandem axle. You can see the tandem axle factors are larger than the values given for single axle, whereas in the case of stresses, the stress factors are more for single axle compared to the tandem axles. Here also we have tables available for different types of shoulders. So, like we have done in the case of fatigue analysis, we can carry out erosion analysis also for a single axle load if you know the magnitude. So, this will be connected to the erosion factor that is selected from the table. Connecting these two, extending this to meet this other line, we get the number of repetitions the pavement can sustain before it fails in erosion damage. So, we can select other magnitudes of single axle also, connect this, find out how many repetitions it can sustain. Similar analysis can be done for tandem axles also. So, if we have axle load spectrum available, different load groups for single axle, the number of repetitions of single axle that are going to be expected, these charts will give us for fatigue analysis how many repetitions of this load group are going to be permissible if it is a single axle. Similarly, how many repetitions of this particular load is going to be acceptable if it is a tandem axle. We know what are the repetitions that are expected, we know what are the repetitions that are permitted. From this we can calculate the cumulative damage. So, let us take a design example. The input data that we are considering is, this is a 4-lane interstate pavement with dowel joints with no concrete shoulders. So, we are not providing any concrete shoulders here. We are providing a 6-inch thick untreated subbase on a subgrade having K of 100 PCA. Modulus of rupture of concrete, that is flexural strength of concrete, is 600 PSI. Expected load repetitions are given in the following tables. For single axle, for different load groups, there is a frequency. For example, the load group having a midpoint value of axle load of 30 tons, there are going to be about 6,000 repetitions. Similarly, a load group having a midpoint of 16 tons, we are going to have about 450,000 repetitions. Similarly, axle load spectrum for tandem axles is also given in the slide. Starting with a trial thickness of about 10 inches, for the 6 inches untreated subbase that we provided, let us assume we are going to provide dowel joints, there is no concrete shoulder. So, the combined K value is selected from the charts that are available from PCA as 140 PCI, MR is given as 650. This being an important road, we will select a load safety factor of 1.2. The design period, let us consider it to be 20 years. For a slab thickness of 10 inches and combined K value of 140 PCA, equivalent stress, this being a case without shoulders, for single axle is 189. So, the stress ratio is 189 divided by 650, which is the flexural strength of the concrete, that is 0.291. Similarly, for tandem axle, the stress ratio is 0.272. Erosion factors for the given case is 2.53 for single axle, 2.73 for tandem axle. So, this table here shows both the fatigue and erosion analysis, because due to single axle loads, axle load group is given here. This is multiplied by load safety factor 1.2. This is the frequency that is expected as given in the previous tables. So, using the charts that I have shown earlier, so these are the expected or allowable repetitions for this load group. For 30 it is 70,000, for 28 it is 160,000, but for smaller loads it is infinite. Similarly, erosion analysis also. So, this is the total fatigue life consumed by this load group. 7.5% is the load life consumed by 28 ton load group, and the smaller loads do not consume any load. Similarly, you have 3%, 1%. You can find out what is the total fatigue life consumed by all the single axle load that are going to be expected. Similarly, for erosion analysis, these are the allowable repetitions obtained from charts. This is the damage that is caused by 30 ton axle load groups, 0.2% is the damage caused by 28 ton axle load groups. Similarly, this is the total damage caused by all the single axle load groups, 20.07 and 2.525%. Similar analysis we will do for tandem axle load groups also. Total fatigue damage that is caused, none of the tandem axle load groups are causing any fatigue damage, but they are causing more erosion damage as expected. So, the total fatigue damage caused by single axle load groups and tandem axle load groups is 20.07 plus 0, that is a total of 20.07, which is of course well below 100%, and the total erosion damage is 2.53 plus 22.73, that is equal to 25.26, which also is well below 100%. So, obviously, the thickness that we have selected is quite safe. However, it is desirable that more trials be made to reduce the slab thickness, because the slab is over safe in this case. We will next deal with the American Association of State Highway and Transport Officials design method of designing concrete pavements. We are referring to the Guide for Design of Pavement Structures 1993. As discussed in the case of design of flexural pavements using AASHTO design procedure, this design procedure is also based extensively on the findings from AASHTO road test, which were conducted in the 1950s. There was an interim guide published in 1972, there is a revised guide in 1981, and there was another one in 1993. There is a draft revision of 2002 version being discussed at present, but the salient features and the design features that we are going to discuss in this lesson will be those which are there in the 1993 version of AASHTO guidelines. There are number of salient features that are incorporated in this guidelines: reliability concept, traffic consideration in terms of 18 kip standard axle repetitions. To convert that, a given axle load into 18 kip standard axle load repetitions, use of equivalent axle load factors, then measuring performance in terms of present serviceability index. We have discussed earlier that present serviceability index at a particular time is obtained from measurements of roughness and distress, which will be in terms of cracking and patching. So, the AASHTO road test equation for present serviceability index for concrete pavements is given as present serviceability index is equal to 5.41 minus 1.71 log 1 plus SV minus 0.09 multiplied by C plus P under root. We discussed about slope variance in the lesson on design of flexural pavements as per AASHTO procedure. Slope variance gives us an indication of how the longitudinal slope varies when it is measured over a small base length of 9 inches. C is the cracked area expressed in terms of square feet per 1000 square feet of paved area. P is the patched area, again expressed in terms of square feet of area, patched area in terms of 1000 square feet of paved area. The one thing that is different in this equation compared to the one that we have used for flexural pavements is, in flexural pavements we have also used the parameter rutting. Obviously, these being concrete pavements, we do not consider rutting of concrete pavements. This is the performance equation which is the heart of the design of concrete pavements using AASHTO procedure. As you can see here, the number of repetitions which is expressed in terms of standard axle load repetitions is expressed as a function of all the pavement parameters and the reliability parameters. Let us have a look at this equation. Log W18 will have the explanation of what all these expressions or parameters stand for. Log W18 is equal to ZR into SO, and another expression in terms of D, which is the thickness of the slab, and another expression in terms of delta PSI, loss in serviceability, and another expression in terms of D, thickness of slab, an expression in terms of terminal serviceability index, expressions in terms of SC, which is a parameter of concrete, CD, drainage coefficient, which reflects the drainage conditions, thickness of slab, J is a parameter representing the joint efficiency, load transfer mechanism, D thickness of slab, E modulus value of concrete, and K modulus of subgrade reaction. So, as you can see, W18 is a function of thickness of slab, concrete modulus value, modulus of subgrade reaction, concrete flexural strength, drainage coefficient, load transfer efficiency, reliability parameter, and loss in serviceability, and of course terminal serviceability value that we consider for designing a given pavement. W18 is the number of 18 kip single axle load repetitions to time t. ZR is standard normal deviate, which corresponds to the level of reliability that we select. SO is the combined standard error of traffic prediction and performance prediction. D is the slab thickness expressed in inches. Delta PSI is the drop in present serviceability index starting from the time of construction. PT is the serviceability at time t. SC is the modulus of rupture of concrete, flexural strength of concrete. CD is the drainage coefficient, which reflects the drainage conditions that would be prevailing. J is the load transfer coefficient. EC is the modulus of velocity of concrete, and K is the modulus of subgrade reaction expressed in terms of PCI. The modulus of subgrade reaction K has to be determined by conducting a plate load test. It can also be estimated from the resilient modulus value of the subgrade material if the resilient modulus value is available. It can be obtained as K equal to MR by 19.4, where K is in PCI and MR in PSI. For combined foundations with subbase placed over subgrade, AASHTO gives us charts using which we can estimate the effective equivalent modulus value of subgrade reaction for the combined foundation. So, that can be done as a function of K value of subgrade and thickness of the subbase and also the material quality of the subbase. Elastic modulus value of concrete can be estimated from its compressive strength using this expression. These are the guidelines for selecting load transfer coefficient J for different types of shoulder and different types of asphalt shoulder, tight PCC shoulder, different types of presence or absence of load transfer device, especially we are referring to presence or absence of dowel bars, whether they are present or not present, and also the type of slab, jointed, plain cement concrete, jointed reinforced concrete, continuously reinforced concrete pavement. The corresponding load transfer coefficients can be selected. This is how we select the drainage coefficient. This is similar to the drainage coefficient that we have used in the case of flexible pavement design as per AASHTO. This can be selected as a function of percentage of time for which the foundation is going to be under saturated condition in a year, and also depending on the rating that we can give to the drainage facility that is available. Once water is there, how fast it can be removed, what are the drainage arrangements that we make. So, accordingly we can select different values of CD depending on the conditions that we have in a given situation. Reliability, obviously for different types of facilities we go for different levels of reliability. The overall standard deviation, which accounts for variability in materials, variability in construction, variability in prediction models, can be selected as 0.34 if traffic projection errors are not considered, 0.39 if traffic projection errors are considered. This is a nomograph that is available for estimating the slab thickness. One can of course solve the performance equation that is given for any given inputs. One can find out the thickness of the slab for a given number of W18 by substituting all the other parameters, but of course that has to be done in an iterative fashion because D appears at more than one place in that equation. So we have to select a trial thickness, compute the W18 value, substituting all the other input parameters. So check whether the W18 value compares with the projected W18 value. If not, we will change the D value, thickness value, and then redo the calculations again. But using these nomographs, we can obtain it directly. How we start with is, we will start with the effective modulus of subgrade reaction K. This is the combined K value. Then these lines, different lines give you R for different modulus of concrete value. Then from this we go up to this, select the concrete modulus value, reach this line, vertical line, and this point will be connected to a point which corresponds to the concrete flexural strength. So connect these 2 points, extend this to a line known as transfer line or transition line TL. After this we select a point on this line which corresponds to the load transfer coefficient J, which we have already selected. So connecting these two, extend it to another transfer line TL, and then you select another point corresponding to drainage coefficient, connect these 2 points and extend it to meet a match line. This is a match line because there is another nomograph which will be matching with this. So starting from this match line, we select a reliability value, rather loss and serviceability value delta PSI, connect these 2 points, let it meet this chart here. Then we start with the selected reliability value, let us say 95%, and then we also select the standard deviation value SO, connect these 2 points and then extend, this meets the transfer line here, and from this point we select the point which corresponds to W18 and then connect these 2 points, let it meet here. So extend these 2 lines like this, wherever these 2 lines meet, that is the thickness of the slab. In this case it is coming out to be approximately around 9 inches. Well, one can solve the equation, or one can also use this nomograph to easily find out the thickness of the slab. Here is a design example. We have to design a concrete slab for the following inputs. K effective is 100 PCA, EC is 5 into 10 to the power 6 PSI, SC is 650 PSI, J is 3.2 for the given conditions, CD is 1.0, PT is 2.5, delta PSI is 2.0, reliability selected is 95%, SO is 0.32, W18 for which we have to design is 10 millions, 10 into 10 to the power 6. Solving the performance equation by trial and error, the slab thickness worked out to be 10.5 inches. The thickness can also be obtained using nomographs. Let us take a few questions from this lesson. What are the main differences in terms of failure or performance models considered in PCA and AASHTO designs? Which are the critical regions for of slab to be considered for fatigue and erosion damage analysis? Do PCA and AASHTO consider thermal, that is curling stresses, in the design of jointed concrete slabs? Let us consider the answers to the questions we have asked in lesson 4.15, which was on design of concrete pavements as per Indian Roads Congress guidelines IRC 58 2002. How to estimate the modulus of subgrade reaction of a concrete pavement? This is with reference to IRC 58. We know that the modulus of subgrade reaction of concrete pavement has to be determined by conducting a plate load test in a particular season, which corresponds to the worst season of the year, using a 750 millimeter dia plate. But if this cannot be done, this value of modulus of subgrade reaction of foundation can be obtained if we know the CBR value of the subgrade. So, IRC 58 gives us guidelines to select the K value of modulus of subgrade reaction from its CBR value. On the other hand, if you also have a subbase placed over subgrade, the combined K value also can be estimated if you know the K value of the subgrade and also if you know the thickness of the subbase that is going to be placed. So, IRC 58 also gives us guidelines as to how to select an appropriate equivalent combined K value for both the layers together. Why is a separation membrane provided between the slab and the subbase? If you have understood the procedures that were discussed for PCA and IRC 58 design procedure, many concepts are similar, but PCA does not recommend use of plastic sheet between the subbase and the slab, which would make it to be a smooth interface. It may not be perfectly smooth, but it will not be roughly bonded. But IRC recommends that for the highway pavements that we have, a plastic sheet has to be placed between the subbase and the slab. The reason for this is the concern for lot of shrinkage failures and cracks that are occurring in concrete slabs because of volumetric contraction and shrinkage. To prevent that, if you provide a smooth interface between slab and the foundation, the restraint that is offered to the slab for its contraction will be significantly reduced. So, when the slab is free to contract, the stresses that are going to be generated will be significantly less. So, the possibility of cracking because of contraction or shrinkage is going to be reduced significantly. What is the critical position of load considered for design of concrete pavement as per IRC 58? Concrete pavement considers the edge position. The wheel load has to be placed in the edge region. This is considered to be the critical position for wheel loads. What is the need for using load safety factor? Because we know in the analysis we multiply the load by a load safety factor of 1.2, 1.1 or 1.0 depending on the importance of the facility. If you are using a load safety factor of 1.2, we are trying to build in more safety into the consideration. We are also trying to take care of those unexpectedly high loads that may come, because we are only trying to consider only the 98th percentile speed, 98th percentile wheel load.